Hello everyone. In this final video, I'm going to be doing some examples of NMR and spec problems, as well as going over some new content that she talked about um, at her final lecture. So just in case you missed that last lecture, she did cover quite a bit of information, and I'm just going to go over that really quickly. All right, so for the first thing that I'm going to show you is mass spectrometry. Okay, so mass spectrometry is just a way of basically getting the mass of a molecule, and it does it in a way of fragments. So the machine is going to read positively charged fragments that are detected by a detector, and essentially it creates these fragments from a neutral molecule by basically shooting these highly energetic electrons at it. So these electrons are going to basically destroy the molecule and break it up into pieces. And so what will happen is so for example, she has over here, we have a neutral CH4. The first electron goes in, and basically it strips away one electron, okay? And so this becomes, ionized. And so what happens is this first electron that is removed from the actual beginning molecule is called the molecular or parent ion, okay? And this is going to be represented on every mass spec graph, okay? And this will be the heaviest and most right peak on the graph. It may not be the biggest peak, but it's going to be the heaviest. And so this is called the molecular or parent ion, okay? And after this point, more electrons will be shot in, and this will break up into more and more pieces, and so on and so forth until, we have really nothing left. Okay? Now some terminology. So we already said the first electron that gets removed. So essentially this first electron, this charged particle that will be read by the machine, essentially going to reflect the actual weight of the whole molecule. And that's because we've only lost one electron at this point, and essentially that is completely negligible mass. An electron weighs almost nothing, and so it's negligible, and so really the mass is concentrated only in the protons and neutrons. So nothing has changed for this mass, and it'll give us the actual mass of this molecule. So now she has this term base peak. Base peak is the strongest peak in the mass spec. It represents the most abundant ion assigned to an intensity of 100%. Other peak intensities are proportional to the base peak, not necessarily the molecular ion peak often represents the most stable fragment. So a bunch of words, but essentially the base peak is let's look at this right here, okay? So this is for the molecule propane, and so propane here has a molecular ion, so it's always going to be number that if there's any number at all, it's going to be the molecular or parent ion. And so this M over Z is 44, and this is the most right peak, therefore it's representative of the actual parent and the original molecule. Okay, so just because it's the like the parent doesn't necessarily mean it's going to have the highest peak. And what these peak means, relative abundance of ions, right? So this is percentage abundance of ions, 20%, 40%, 60%, 80%, 100%. So what we're going to see is the 100%, or aka the base peak, is always going to be the fragment that is the most stable fragment. So sometimes the parent is the base peak and it is the most stable fragment, and a lot of times it is not. So the parent is this peak right here, but the most stable fragment is actually this one. So some other peak around like 29 or 26 or 28, something like that. So this is directly correlated to stability, okay? And if we look over here, we have propane, we have the charged molecular ion or parent ion, and it can essentially be cut into different pieces. So either I get a CH3CH2 piece that is a positive charge, and then I get a CH3 piece that's has the radical, or the other combination, I get the CH3CH2 piece that has a radical, and the CH3 has a positive charge. So this is how it'll always split up, and then it'll keep breaking into more and more pieces as more and more electrons are fired at this molecule. Okay, and so the base peak is going to actually be representative of this CH3CH2 right here, and I'll tell you why. So when it comes to radicals versus carbocations, which one is more unstable? The carbocation is more unstable. Okay, so carbocations are more unstable than radicals, and that's because they have, a complete deficiency of electrons that were previously there, whereas a radical is half electron. Okay, so this one, carbocations are more electron deficient, therefore more unstable. And so therefore we need to compare the two carbocations, and we want the one that is more stable. So carbocation stability is dependent on the number of carbons that are bonded to that carbocation, and therefore the CH3CH2 with the carbocation right here, this is a primary carbocation, and this right here is basically a 0-degree carbocation. It has no other carbons attached to it. Therefore, sorry. Therefore, this is the more stable, and therefore it is the most abundant. And it makes sense, right? These molecules are being, broken up into these fragments, and just from basic stability, the fragment that is the most stable is going to be the most likely to form. So, out of all these charged particles, the more stable fragment is going to be the most common to form in this process. So that's why it is the biggest peak and the most abundant, and it's given the 100% abundance value. Okay, and everything else is scaled relative to it. These are not too important to understand, but it's just some concepts to understand how mass spectrometry works. And then there's high resolution mass spec, which essentially this will give us the mass. It'll give us 44, but for example, there are many things that could be very close to the mass of 44, like C3H8, C2H4O, CO2. All these have very close masses to 44, 44.06, 44.026, 43.98, 44.037. All these are really close to that. And essentially, high resolution mass spec will actually give us a reading that has, some decimal places. So it's very accurate. And so it'd be very easy for me to figure out which compound exactly I have. So if I did this same molecule in high resolution mass spec, it gives us a value of 44.063, and we can very clearly see that this most closely correlates to this molecule right here, the C3H8, which it is. So 44.063. So it almost exactly, essentially, just rounded. And so we know for sure the C3H8 and not these other ones. Okay? So now we need to look at isotopes. And this is what's really the most important thing on your exam. So there are 4 isotopes that you need to be very familiar with. And what these M and M plus 2 values means just that there's M plus 1, so mass plus 1 and M plus 2. And this means that we have isotopes, and some isotopes are, one, either a proton. It's the number of I believe protons. I think protons are neutrons. I think it's neutrons that they have that's different. So regardless, it's going to be one heavier, so one molecular weight heavier, and so that's what the M plus 1 means, or M plus 2, whereas sometimes it's 2. See, so M plus 1 or sometimes M plus 2. Not very important. That just means it's going to be shifted to the right. So in nature, many atoms have isotopes, right? So let's just look at a few. Okay. Let me just open up the sketch pad. So let's just look at a few isotopes. So we have bromine, chlorine, I, and I'm not going to do I actually first. Sulfur, and iodine last. So for bromine, bromine has 2 equally likely isotopes that are found in nature. They're 50-50. Okay? We don't need to know them. There's one's 79 and one's 81. They're about 50-50. Chlorine has one that's 75% found, and the other one is 25%. Okay? And then sulfur has one that's 95%, and then it has a 4% one, and then it has a 1%. And all these numbers are very nicely, given here. So 95, about 1, about 4. Okay? So pretty simple. And then iodine is something that I'll talk about after I finish talking about all these three. So essentially what this means is, for example, if I have a molecule that has a bromine on it, okay, they're putting this into the machine, right? They're putting a certain amount of moles of this. So aka, we have millions of these molecules, right? We have moles of it, right? And so, of course, I'm going to have, there's no way to control the isotopes that I have in it, really. We're not selecting against the isotopes. So we have these isotopes present in their statistical, chance of them being present. So I'll have 50% of these will be the 79, and another molecule that looks exactly the same has a bromine, but it might be the 81. So I have 50% likely to have both the 79 and the 81. And these will show up on the spec because this molecule weighs this one right here weighs 2 more than the 79. And so we'll see that actually on the mass spec represented very clearly. And the same thing goes for all of the other ones. Okay? We'll just see these in different ways. And I'll show you how these numbers, 75, 25, 95, 4, and so on and so forth, are represented. So let's just look. So you have a molecule that has a bromine on it. And what we're always going to see that's characteristic of bromine is that we're going to have always two almost equivalent intensity peaks, right? So we have the 79 and we have the 81. And both of them, since they're both like 50%, 50%, we're going to see these almost equivalently sized peaks, right? Because 50, we have equal intensity of both of them being present. It's just abundance. So equal abundance of them both because 50% is they're both 50% as likely. So it's very simple to understand. And obviously, you might have many of these double peaks because what if I break my molecule, like let's say right here, and I get a CH2Br fragment and I get a CH3CH2 fragment or whatever fragment. Obviously any fragment that has a bromine on it, it's going to be represented by those double peaks. And so that's what you'll see, and that's what's characteristic of bromine. So you need to be very familiar with the double peak. Now let's look at chlorine. Chlorine has 75% and the 25%. So you'll see essentially a peak. So this is the most furthest peak. Then you'll see a peak that, this one right here, I'm going to zoom in a bit. This one right here, where the arrow is pointing, it looks about 25% the size of this one right here. And so it looks like a third of the size almost, right? And so this is 75%, this is 25%. And so this you'll have these two main peaks for chlorine. And that's just something else you identify. So not too bad. And then finally for sulfur, if anything has sulfur, essentially you see a very big main peak, and then you see these two smaller ones. And so you have, one is like 4% and the other one is 1%. And so you have like these kind of always these three peaks. Okay? And the question's always going to be what atom is also on this molecule, and she'll give you maybe something that looks like this, maybe she'll give you something that looks like this, maybe she'll give you something that looks like this, right? And you just have to be able to identify them and what they look like. And then finally, the last one is iodine, okay? Iodine, I'm going to talk about it very quickly. It has 100%. There's only one form of iodine, right? Iodine. So what happens though when it enters the mass spec machine, if I have a molecule that has an I on it, iodine, this essentially it fragments off, and what I get is I get both the main parent molecule, and then I also get these positively charged iodines, idoniums, I think what they're called, that are also detected by the machine. So iodine or iodonium, whatever, has a weight of 127. So essentially, what you're going to see is you're going to see a peak at 127 always, and you're going to see the peak that is 127 And let's say this weighed X. So you're going to see at 127 plus X peak, you're going to see X, and you're also going to see 127. All right? So just to show you by what I mean, so let's say the total weight, the parent molecule that contains the iodine and everything else on it, weighs 156. The iodine will break off, and you'll have the 127 peak that reflects just the iodonium or whatever. You'll always see a 127 peak because it's how much it weighs. And then you'll see the peak that is essentially 156 minus 127 equals 29. So this is everything else that was left after the iodine broke off. And so this is the remaining weight of the molecule. And you'll always see these three characteristic peaks. Okay? And that's pretty much it. And here's just some more examples. There's other examples that she has. This is just a molecule where you see 50-50, 50-50, 50-50, 50-50. And these are all pieces where there's bromines on them. And so this is just the characteristic pieces and looks of the of a molecule that has bromine on it. Okay? So it's pretty easy. Just make sure you're familiar with the four. All right? The last thing is going to be C13 NMR. C13 NMR is extremely easy. It's the same exact rules as proton NMR, except there's two types. There's proton spin decoupling and there's off-resonance decoupling. Proton spin decoupling, all carbon signals appear singlets. So C13 NMR, essentially, it allows us to identify unique carbons. So I don't need hydrogens to be present in order to identify them on the C13. Okay? So if I have something like this, I have one unique carbon over here, two unique carbons over here, 3, 4. And on the C13, I would see 1, 2, 3, 4. All right? I would see 4 peaks, and this would tell me, oh, I have 4 unique carbons. And that would be represented by here. I have 4 unique carbons. And that's what it is. Every single carbon that is unique will be represented on the C13 NMR. Okay? And then for off-resonance decoupling, you observe splitting. So there will be splitting by other carbons. So if I say this carbon, once it's off-resonance decoupling for C13, I just count the number of adjacent carbons and I just add 1. Okay, so n plus 1 rule. So this one, the n plus 1 value for this one will just be, I have 1 unique carbon next to it, so it'll be 2. And then I look at this one right here, it has 2 unique carbons next to it, so 1 over here, so 1 plus 1, I believe. And then I just, so instead of multiplying them together, I believe you just, they are added. So I have 1 over here, and I have another unique over here, so I have 2 plus 1. So instead of multiplying them individually, you just add them up. So I have 1, 2 unique groups, and then plus 1, so that's 3. So this is going to be triplet. And then I have CH2 group over here, so it's the same thing. One group over here that's unique, and 1 group over here that's unique. And so that's 2 plus 1, that's also 3. And then CH3 only has 1 unique group, and it's at CH2, so it's 1 plus 1, that's 2. So it's not too complicated. It's pretty straightforward, and it's just you're looking at the number of unique peaks. Okay. So yes. So just the number of unique peaks, and that's all it will really tell us. All right. So let's see. Any other examples? Okay. So let's see. All right. Not too bad. So normally I don't ever use a C13 NMR, but it can be kind of helpful to tell you how many unique carbons. And the max that you're going to be responsible to do is it'll show the C13 NMR graph, and then it'll show like a number of peaks, and that number of peaks that you see are going to be the number of unique carbons. Okay. So now I'm just going to do some practice with you guys and just do some problems. I have quite a few to do with you guys. So only 4 examples. I'll try to do it as quickly as possible. So first step in any problem, and saturation number. Saturation number is, for this one, is 5 times 2, that's 10, plus 2, minus 2. So that's now I have 0 on the top divided by 2. So my unsaturation number is, my bad, it should be 10 times 12 minus 10. So it's 2 divided by 2, that's 1. Okay? So my answer is 1. Alright? So my unsaturation number equals 1. It's simple math. And then now I'm going to go to the IR, and what I see over here, this is 1500, this is 1600, 1700, 1740, 1750 area. I see a peak right here. It's very sharp, very deep. So this is going to be the carbonyl for sure. Okay? And so this is my 1 unsaturation value, and this is also my oxygen. So I have a lot of things figured out already. Now I'm going to look at my NMR, my favorite part, and now I see this 4H and my 6H. So whenever you see either 4H, 6H, 9H, these are going to mean that you have symmetrical structures. Either symmetrical structures, I did one on the 2016 exam, that's one version of it, or things like, for example, 6H usually means you have an isopropyl. You have 2 CH3s, and then you have, whatever hydrogens over here. And that usually is indicative of some sort of isopropyl or isopropyl looking like thing, right? Like this. Other type is if I have like groups like this, and I have symmetry, all these groups are symmetric around this one environment right here. And so 6H could also mean 3 CH2s, right? 6H could either mean 3 CH2s or 2 CH3s, coming off of some molecule. Okay? Just re-listen to me what I just said, okay? So these are just three examples of types of symmetry, and this will be identified by the integration number. Anyways, we have symmetry here, right? And I know I for sure have symmetry because I have 5 carbons and I only have two peaks. So this is definitely not just representative of 2 carbons, it's representative of at least 4 carbons. It's definitely, at least total of 4 carbons. Okay? 1 carbon is going to be given away for the carbonyl, so I have 4 carbons left to work with. So that means these 2 peaks have to represent at least all these remaining carbons, hopefully. So let's just get to it. So I have 4H, and so my hypothesis is going to be that they're CH2s. So it's a CH2, and it's next to so I have 1, 2, 3, 4. So 4 minus 1 is 3. So it's a CH2 next to a CH3, right? And essentially what this is saying is that I have 2 of them, and they're symmetric. And essentially this integration number is just adding up the total of these 4. If you don't understand how integration number relates to peaks, essentially it's an integration number is going to relate, it's going to relate all the hydrogens that correspond to a certain chemistry. So let's say let's say all I had was this bonding that was left. Okay, let's say this was my whole molecule, for example. And let's say that, there were no hydrogens over here, okay? Let's say this was my molecule. The reason why these H's are going to be added together is because they only correspond to CH3. So I have a particular chemistry here where I have a CH2 that's bonded to this, and this one's also bonded to this, and they're both bonded to CH3s. So because they have the same CH3 environment, they both have the same splitting, right? And so therefore, we're going to sum those protons together, and they both correlate to the same environment. So this is the integration number is telling us all the total amount of hydrogens that correlate to a specific type of environment, and that environment is the CH3 environment. So I hope that makes sense. I'm going to move on now, though. All right, so this is my current guess. I have 2 of these, and then the 6H I have is always pretty indicative that I have a CH3, and I have 1, 2, 3, so 3 minus 1. So meaning I have it next to a CH2. Wow, so now my 2 pieces correlate together. I just guessed that I have CH2s next to a CH3, and this is telling me I have a CH3 next to a CH2. So I'm guessing they are going to be together. And now I pretty much have everything I need. I just said that this is likely representative of half the total number of carbons, right? That's why, we have this double number because they're symmetric, right? If things are symmetric, they're not represented again. They're just represented once, but we might see this representation via the integration value. So I have a carbonyl. I have symmetry. I know I have a CH2 next to a CH3. Let me do this in line angle, it's much easier. So I have a carbonyl. And so essentially what my molecule looks like, it looks like this. So I have a CH2 next to a CH3, right? And I have two of them. So the carbonyl is in the middle, splitting them in half and making this symmetric. And essentially I have two CH2s that correspond to the same CH3 environment. So therefore, that's going to be representative of the 4H. And then I have two CH3s that are representative of the same CH2 environment. And so that's going to be a total of 6 hydrogens that correspond to this particular CH2 environment. And that's how we get this answer. Okay? Work with it, re-watch it, think about it, and you'll eventually make a lot of sense. All right, let's move on. C5H10O. So again, we have a same formula. I have a saturation value of 1. And then again very quickly see the carbonyl peak. All right, now let's go on to our NMR. First thing, I'm going to go from left to right. I have a CH. And what I see here is that it looks pretty complicated. I have 1, 2, 3, 4, 5. When I see things that have more than 4 peaks, I'm immediately going to tell myself, stop, don't think about it. This looks like a lot of peaks, and therefore I think it's around many carbon-hydrogen environments. So I'm going to think that this is around many things that have hydrogens on it. And so I'm going to leave this for later when I have more, when I try to gather more information. So I'm going to think that this is in between, two distinct carbon-hydrogen environments, and that's why it's so many peaks. All right. Then I have a CH3, right? So integration number 3, and it's by itself. So therefore, it's next to no other things, right? No other environments. And then finally, I have 6H next to 1, 2, so next to a CH. All right. So essentially, it's saying I have a CH3 bonded to a CH, and this CH is also bonded to another CH3. So I have two symmetrical CH3s bonded to a CH. And this is the most common, actually, what you see. The ones I just did, this is kind of, the harder type of symmetry. This is the easy type of symmetry, right? The isopropyl, right? Isopropyl have the carbon, the CH3, CH3, and they just kind of look like that. Isopropyl. This is the most common one. So this is what I suspect we have over here. And so now that I kind of have more information, I kind of can deduce that this CH is corresponding to this right here. And this complicated many peaks is corresponding to the many CH3s that are surrounding it. Okay, that's why it's so many. And so now I have enough information to build my molecule. So I have a carbonyl, I have a lone CH3, and so what does that mean? The only way that I can have a lone CH3 in this straight chain is if it's secluded by the carbonyl. So the CH3 is going to be over here at the end, then I have the carbonyl, all right, and then I have the rest of my molecule. So I have my CH3s like that, all right? So this is the CH right here. Okay, I'm going to use a different pen. This is the CH right here. This is this one that's secluded by the carbonyl. And then this is this one that's combined from that right there. Okay? So hope that is very easy to see. All right? Easy peasy. And this is the correct answer. All right, let's move on. All right. Now, C9H12O, unsaturation number is 9 times 2, that's 18, right? 18 plus 2 is 20. 20 minus 12 is 8. 8 divided by 2 is 4. My unsaturation number is 4. So this is highly indicative when I have 4 or more that I have a benzene ring, right? A benzene ring contains 3 unsaturation numbers from each double bond and then 1 unsaturation number extra for the ring. So this is completely represented by the benzene ring. And this is confirmed by looking at the 7 to 8 region on the NMR, and I clearly see I have a benzene peak in the 7H, and this is indicative. All right, now let's look at my my IR really quick. I have an oxygen, and I see a pretty wide, pretty clean stretch over here. So this is going to be indicative of the OH group. All right, I have 1600 region. I have something over here. This is just at the very edge of the 1600. So this is not really anything. This is just part of the fingerprint region. It's not part of anything. And I know I don't have any carbonyls or alkenes because I've already used up all 4 of my unsaturation value on the benzene ring. So I don't have anything else that I can use. And so I know this is garbage, and I know this has to be an alcohol. Okay? So that's definitely an alcohol because I have this stretch. Now let's go to the NMR. Okay? So in the NMR, I have a 5H value for the benzene peak. That means my benzene is saturated with 5 hydrogens. And so that means, so a benzene without anything on it has a total of 6 hydrogens on it, right? Each carbon has 1 hydrogen. Each substitution I do on the benzene ring, it takes away 1 hydrogen. So therefore, if I have a total of 5, that means I have a mono substitution, right? A benzene ring that only has 1 group on it, right? And so that is very helpful. So I have this figured out. So I know I have a mono substituted benzene ring. Now let's look at the other things. I have a CH2, and it's next to 1, 2, so 2 minus 1. It's next to a CH. I have a CH that looks very complicated, and I'm going to say it has, question mark, things around it. It's complicated. And then I have a lone CH that this looks like a lone CH, okay? I'm going to put it on my radar. I'm going to think about it. CH next to nothing. And then at all. And then I have a CH3 that's next to 1, 2, next to a CH. Okay? So this kind of seems to confirm each other. So I have a complicated CH, I have a CH2 next to a CH, and I have a CH3 next to a CH. So I'm going to guess that all these pieces are connected to each other. So I'm going to guess that the CH2 is connected to CH, and this CH3 is also connected to the CH, and this CH is being complicated because it's next to both a CH2 group and a CH3 group. And so I'm going to start thinking about my molecule now. Whoops, didn't want to do that. All right, so I'm going to start thinking about my molecule now, and I'm going to draw my benzene ring again. Not a very good benzene ring. Okay, I drew it even uglier this time. All right, the circle, and I'm going to have my 1 group coming off. All right, my first guess is that I have the CH2 that's right here. Okay. Then I'm going to guess that I have this bound to the CH. And then I'm going to guess that I have the okay. Now I'm going to check this over at the end. Okay. I'm going to guess that I have the CH right here. Okay. And then I'm going to guess that I have the CH3 coming off of it. And then I'm going to guess that I have an alcohol right here. I may not be right yet. I need to double check. So there's one thing I failed to pay attention to. So one thing I failed to pay attention to is where the CH2 peak is. And the CH2 peak falls in the high 4 region, right? So it's past 3.5. That means it's bound to an oxygen. And so what I have over here is a CH2 that is also bound to the ROH. Okay? And this mystery peak right here, so the first thing I need to count my carbons, right? I have 6 carbons from the benzene, right? So 6 carbons from the benzene, 1 carbon, so that's 7, another carbon here, that's 8, and then 9. So I already have 9. So that means this extra peak right here is actually not another carbon, right? It's actually our alcohol. And alcohols are always going to be singlets. They're singlet 1H's. Sometimes they're short, sometimes they're really tall like this. This is actually strange looking. It's not usually like this, but usually it's short, but it's always a singlet 1H. And so this is my alcohol right here. Okay? So two things we need to correct. My CH2 is bound to a CH, and it's also bound to the alcohol. Okay? So what this means is that I need to rectify my molecule here. Okay? So that means that instead of this setup, so to make the OH possible to be bound over here and still have this CH have enough bonds, what I have to do is I need to essentially I'm going to rewrite it over here. So this is wrong, right? This is just my guess. Guessing is perfectly fine, right? Let's us go back and check and make sure we did everything right. So I'm going to now draw the correct structure. So now the correct structure is actually going to be with the CH bound first. Then I'm going to have, a CH3 group. So let me actually draw that hydrogen out. Right? So one hydrogen like this. I'm going to have a CH3 group like this. And then I'm going to have a CH2 group like this. And then on the CH2 group, I'm going to have the OH. And now this is fully reflective of my actual molecule. So I have a CH2 bound to an OH, which is right here. So let me get the red color. So this is right here. All right. This is right there. This is right here. I hope you can see. Right there. And this one right here is that one. Okay? So I hope you can see where each one is coming from. All right? Now I'm going to move on. All right, so C9H10O, so it's going to be 18 plus 2, 20, 20 minus 10. 20 minus 10 is 10, 10 divided by 2. Unsaturation number is 5. Okay, so that means I have a benzene ring and one other type of unsaturation. So double bond, ring, another ring, which is not likely at all. We won't have two rings. We already have a benzene ring or carbonyl. So if I look into my 15, 16, 17, I see I have a 1700 peak, and that's going to be representative of a carbonyl. Okay, so this confirms that all 5 unsaturation numbers now. Okay, and this is the oxygen as well being confirmed here. I have no OH peak, right? So this is not here. So this is definitely not an alcohol. Okay, so now let's start looking at the NMR. First thing, the benzene is going to be corresponded to the 7 to 8 region here. So this is 7, this is 8. And in it, I see a total of 4 hydrogens. And I see these 1, 2, 1, 2. So doublet, doublet. So whenever you see this doublet, doublet, and it can look like this or it can look like this. 2H, 2H. And what this always means, so you have mono, and now you have para. Mono is 1 substitution, para is 2 substitutions. So a group on the top, and then on the opposite side, you have another one right here. So this is what we have, okay? And even more indicative, I have another indicative group, in the 9 to 10 region, so always in the 9 to 10 region, if you have a peak in the 9 to 10 region at 1H peak, this means I have an aldehyde. An aldehyde is represented in the 9 to 10 region of the NMR. Okay, very important. Okay, and then now let's look at the other things. So I have a CH2, and it's next to 1, 2, 3, 4. So next to a CH3. And then I have a CH3 that's next to 1, 2, 3. So 3 minus 1, that's 2. So it's next to a CH2. These two correspond to each other. So this peak and this peak are confirming each other, and they're next to each other. They're little buddies. Okay. So now I have to figure this out. So one thing important to note, which is obvious but good to note, is that aldehydes and CH3s are always at the ends of your molecule. An aldehyde is always, it has to be at the end, right? Because the hydrogen is sticking out. There's no other bond. So this is a terminal position. So basically you need to think, okay, wherever I put the aldehyde, it's going to be at the very end. It's going to terminate everything else. It's going to terminate whatever chain I'm about to do. So this is going to be at the end, and this is also going to be at the end. So essentially, this should make you think, oh, I have two ends. So I have a CH3, which should be on one end, right? And I have an aldehyde, which should be on the other. So essentially, that should tell you that my aldehyde is on one side, and my CH3 is on the other side. Right? That's the only way it's possible that I can have two ends. Obviously my aldehyde and my CH3 cannot be on the same side, right? Unless I have some sort of, unless I had a CH and then I had, the aldehyde like this, and then I had like a CH3 like this. That's the only case, but I don't have a CH like this. I have CH2, CH3. That is not the case. So that means they have to be on, one is on this end and one is on the other end. And so what we have to think is, essentially, it's not much left for me to do here. I have a benzene ring, and then on one side, I have the aldehyde, and then on the other side, I have a CH2, CH3. And it looks like this because I have to have these two guys together. I have to have the CH2 and CH3 next to each other, okay? And if I don't have them, next to each other, then I wouldn't have these splittings, okay? I would not be getting these readings. So they have to be next to each other. And therefore, I cannot have them on the other side, right? I only have these two groups. I have an aldehyde, and I have the benzene ring. So 6 carbons in the ring, 7, 8, 9. So all 9 are accounted for. They have to be over here because there's no way for me to fit a CH2 and bring it over here. I cannot have this structure, for example. This would be wrong. If I have this, I'm just going to do it like this. So let's say I have this. This is wrong, and then just a lone CH3 on this side. This is wrong because we said that the CH2 and the CH3, they are splitting each other. They have to be next to each other. Okay, so they're not next to each other in this one, so this is wrong. Okay, this is the only structure that represents everything correctly. All right, so take the red pen. Aldehyde is represented right there. This para-substituted benzene ring is right there. The CH2 is right there. And then the CH3 is right there. Okay? And so everything is represented correctly and nicely in this structure that I proposed. Okay? So I hope that helps kind of the logic and thinking about it. Just, you have a couple more hours left to study and get a good night's sleep. Message me if you have any questions. I will do my best to answer them as fully and properly as possible. All right. Best of luck, guys. I believe in you. You got this.